All right, folks, this is we're going to get started with page 2 of the section 4.2 notes. I want to make a quick comment, though. When you start doing WebAssign for section 4.2, you're going to notice that they ask you to pick a graph that matches a rational function, and it's a multiple choice question, and there are 4 options. So I'm not naive enough to think that you can't just guess and check your work because you get multiple attempts on each question. However, you're not learning anything if you do that. I want to encourage you to actually do the analytical work to determine what the graph looks like. And that's really the point behind this entire lesson. I know some of you skeptics out there are saying, why should I bother with this if my graphing calculator can give me a beautiful picture like this every time I need to graph a rational function? Well, it's the same reason why in a language arts class we analyze literature. It's to develop a deeper understanding of what is going on with the function beyond just knowing what the picture looks like. Okay, so that's enough about that. Let's go back and get started with the notes for page 2. So there are just 2 examples here on page 2. We're going to graph 2 different rational functions, and I'm going to go through that procedure that's on the front page to determine all the different features, and then we'll see what the graph looks like. Okay, so first thing I'm going to do with this function is I'm going to factor both the numerator and the denominator, because I know that in order to find where things equal 0, it's easiest for me to have that in factored form. The denominator is pretty easy. That's just going to be x minus 3 times x plus 2. Numerator is a little more challenging. I'm going to go ahead and show you one example like this because I know some of you are going to, if I just write the answer there, you're going to be like, how in the world did he get that? So we're going to go 2x squared minus 3x minus 5, 2x squared minus 3x minus 5, and I'm going to use the diamond factoring method, something that I've talked about before. I'm going to multiply the first coefficient and the constant, so that gives me a negative 10. And then I'm going to write the middle coefficient down here. So I'm looking for factors of negative 10 that add up to negative 3. Well, that's negative 5 and positive 2. Negative 5 times 2 is negative 10. Negative 5 plus 2 is negative 3. Now here's the interesting part. I'm going to divide each of these by 2x. I'm really not dividing by 2x. I'm just doing it in this form to kind of show me what the different factors are. So this simplifies to 1 over x. So that's going to be a factor of x plus 1. This one does not simplify, so this is going to become a factor of 2x minus 5. So 2x squared minus 3x minus 5 equals the product of 2x minus 5 and x plus 1. Okay, so now that I have my rational function in both the numerator and denominator factored, I can think about I can start thinking about how the function behaves. So I know from the numerator that f of x, the whole function, will equal 0 when x equals negative 1 and 5/2. Okay. I also know that my denominator will equal 0 at a couple places, so that means f of x will be undefined. At x equals negative 2 and positive 3. Okay. So let's start thinking about our procedure. I'm going to first talk about the domain. The domain of this function is x cannot equal negative 2 or 3. X-intercepts, those are my zeros. My x-intercepts will occur at negative 1 comma 0 and 5/2 comma 0. My y-intercept, well, y-intercept is what happens to the function when you plug in 0 for x. So if I plug in 0 for x, it's going to be -5 divided by -6. So that gives me the point 0, 56. Okay, moving on. Let's talk about any vertical asymptotes we have in this function. Vertical asymptotes will occur when my denominator equals 0, as long as that factor doesn't cancel out with 1 in the numerator. That does not happen, so we'll have a vertical asymptote at x equals -2 and at x equals 3. Those are vertical lines, the equations of vertical lines. Let's talk about horizontal asymptotes now. Horizontal asymptotes. In order to determine if there's a horizontal asymptote, I have to look at the degree of the numerator and the degree of the denominator. Well, those two are equal because I have a 2x squared there and an x squared there. So what happens when we have the degree is the same in the numerator and the denominator? We look at the ratio of those two coefficients. So that's going to be 2 divided by 1. So the equation of our horizontal asymptote is y equals 2. All right, so we're getting started here. We got a lot of analytical work here, but we're not quite ready to graph the function yet. Next thing I want to do is create a sign chart for this function. So for my sign chart, I'm going to start with, I put f of x on the top and x on the bottom. I've got to draw my number line. I don't need 2 number lines, just 1. Thank you. So for my sign chart, there are 4 different numbers I have to highlight on the number line. That's my domain restrictions of -2, and +3. Remember, for those domain restrictions, we mark them with a unique symbol, not a 0, because the function does not equal 0 at those values. The function is undefined. And then I do have 2 zeros for the function. That's when my numerator equals 0. That occurs at -1. And then again at 5/2. Okay, so let's construct this sign chart. And I'm going to kind of go through this one quickly. If you need to go through it a little bit slower, I'm going to encourage you to actually pick test points and test on each of these intervals between the numbers on our sign chart. So I'm going to start by picking thinking of a number that's greater than 3. If I'm greater than 3, this is going to be, let's pick a number like 4. 2 times 4 minus 5, well, that's positive. 4 plus 1 is positive. 4 minus 3 is positive. And 4 plus 2 is positive. So all 4 of these factors are positive if I'm out here to the right of 3. When I go to the left of 3, the only one that turns negative is this guy right here, x equals 3. So the other 3 are still positive, and this one is negative. So my sign chart's going to be negative on this interval. Keep in mind, this x minus 3 will stay negative for the rest of the number line to the left of 3. What happens as I cross over 5/2? Well, now this one turns negative. 2x minus 5 turns negative. Pick up test point there like 0. 2 times 0 minus 5 is negative. So 2 of these 4 factors are negative, but 2 are still positive. End result there is a positive value, positive output from the function. Now let's cross over x equals -1. Well, this term is now going to be negative. So I have 3 negatives and 1 positive. My function is back to a negative value. Cross over x equals -2. Now this factor becomes negative. 4 negatives give me a positive. So there's our sign chart. That's the thought process I go through mentally when I analyze a function and construct a sign chart. If you're not quite that quick with it, that's okay. Take a little more time and actually pick some test values for your calculator. Let's go ahead and graph this thing now. Alright, so I have my axes drawn in now. What I'd like to do is draw my vertical and horizontal asymptotes. So I have a vertical asymptote at x equals -2. I have a vertical asymptote at x equals 3. And then I have a horizontal asymptote at y equals 2. Okay, so I'm just going to quickly label these things for us so that we don't forget what they are. Here we have the line x equals -2. This is x equals 3. And this is y equals 2. Okay, so remember at the ends of the function, out here towards positive infinity and out here towards negative infinity, we approach our horizontal asymptote. In between the vertical asymptotes, though, we don't care if we cross the horizontal asymptote. That's just something to keep in mind. So let's look at our sign chart. Out to the right of x equals 3, our function is positive. Well, we're bounded here by a horizontal asymptote to the right and a vertical asymptote to the left. So the graph of my function there is going to look like this. All right, so we are one step closer to having this function graphed. All right, now let's take a look at what happens between x equals 3 and x equals -2. Well, we have some points we can actually plot for this function. We have some x-intercepts. One of them is at -1, 0. We have also one at 5/2, 0, and 5/2 for those of you decimal fans is 2.5. And then we have 0,56 as a y-intercept. So 0,56, it's going to be right about there, just below y equals 1. Okay, so I have those points on my graph. I know that just to the left of x equals 3, my function is negative. So I have a very small band here between x equals 3 and x equals 5/2 where I'm negative. And then the function goes positive from 5/2 to -1. And hopefully you can see it's going to go through that y-intercept. And then it goes negative again. So let me try and sketch this for you. That's what that graph's going to look like. Okay? So again, how do I know that? Because I'm using the behavior near the asymptotes, I'm using the sign chart, and I'm using the points that I was able to plot. Folks, I'm sorry, you do deserve better than that. I'm going to try and do that better. So we're going to come up here. That's a little better. We'll go with that. Okay. Now let's look to see what happens with the rest of our sign chart. So now we're going to move over to the left of this vertical asymptote x equals -2. My function is positive. I'm bounded by, on the right-hand side, by this vertical asymptote, and on the left-hand side by this horizontal asymptote. So this is how the graph is going to look out here. Okay, folks, congratulations. You just graphed your second rational function. I would encourage you to check these on your calculator and see if they match up with what we've done here. This one, to be honest, I probably was a little bit too extreme there. That thing's going to come down and maybe do a little bit more of this. That's a little better. Okay, folks, again, why are we graphing these by hand? It's so that we understand the behavior of the function a little better. I know that you can create these same graphs with your graphing calculator, but you certainly wouldn't have the same depth of understanding about the function as you do now. All right, we got one more example to do here. I'm going to... This one is a little bit more challenging than the previous one, so hopefully you don't get too lost with me here. Take a look at that numerator. Okay, first of all, it is a cubic function. And we don't have any tricks to just directly factor it cubic. So what we have to do is we have to look for possible zeros. And I will tell you, just to get this thing jump started, that there are zeros at x equals -1 and x equals -1/2. So all of the techniques we learned in the last chapter about factoring polynomials, finding zeros, using long division, and factoring a polynomial, those are the same tricks that apply here. And just in the interest of time, I'm going to tell you that this one factors into x plus 1 times x plus 1 times 2x plus 1. My numerator, that's just a simple quadratic to factor. That's going to be x plus 2 times x plus 1. Hopefully, now that you see that factored, you notice something happens here. We've got a pair of factors in the numerator and denominator that cancel. That should tell you something about the behavior of the function. Just to make a note up here, I know that f of x will equal 0 and x equals -1 and -1/2. F of x will be undefined at x equals -1 and -2. Oh, there's a problem. So I can't be both 0 and undefined. So I got to cross out this value right here. The function will not equal 0 at x equals -1 because that's a factor that canceled. The function will be undefined at x equals -1. All right, let's take a look at the domain of this function. The domain of this is going to be x cannot equal -1 or -2. X-intercept of this function, that's wherever the output will equal 0. That's x equals -1/2. The y-intercept of this function, well, let's see, that's f of 0. If we take a look, if we plug in 0 to this function, we have constant of +1 divided by +2, so that's going to give us an output of 1/2. So our y-intercept is 0, 1/2. We're going to have a vertical asymptote at x equals -2. That's this guy right here. But what happens at x equals -1? Well, because we had a pair of factors that canceled in both the numerator and the denominator, that means I'm going to have a hole. So we're going to have a hole at x equals -1. And if you recall, the way to find the y-coordinate of the hole is to plug back in x equals -1 to the remaining factors. So if I plug back in x equals -1 to my numerator, I'm going to get -1 plus 1. That's 0. This is going to be 2 times -1 plus 1. Well, that doesn't matter because the one on the left here is 0. So I have 0 times some number, and then x plus 2, that's going to be let's see, that's going to be just 1. 0 times some number divided by 1 is just plain old 0. So the y-coordinate of my hole is 0. So let's talk about asymptotes now. Does this thing have a horizontal asymptote? Well, I got to take a look at the degree of my numerator and the degree of my denominator. I have a cubic divided by a quadratic, so I'm not going to have a horizontal asymptote, but I am going to have a slant asymptote. Okay, and the slant asymptote is going to be the quotient of the polynomial division, numerator divided by denominator. So let's just take a look at that real quick. All right, so I did a lot of polynomial long division there, and I end up with a quotient of 2x minus 1. I don't care about any of this other stuff because all I care about is the quotient. The slant asymptote is going to be y equals 2x minus 1. All right, folks, we're almost ready to graph this. We just need to create a sign chart here. We're going to go f of x on the top and x on the bottom and see what we get. First thing I'll do is mark my domain restrictions. I have -2. That's a domain restriction. That's the location of a vertical asymptote, so I'm just going to note that down here. That's a vertical asymptote. I also have a domain restriction at x equals -1. That's the location of a hole. Last but not least, I have a 0 at positive. Oh, don't forget to mark that with an identifying mark that says it's not a 0. And then at x equals 1/2, we have a 0. Okay, so let's go through this sign chart and figure out what happens. Notice that this factor of x plus 1 in the numerator and the denominator, those factors cancel each other out. So if they're both positive or both negative, it doesn't matter. They have no effect on the sign chart. The only factors I need to look at are x plus 1, 2x plus 1, and x plus 2. So we start here to the right of x equals 1/2, and they're all positive. That's great. So we're going to mark a positive on our sign chart here. When I roll across between 1/2 and -1, 2x plus 1 turns negative. So x plus 1 would be positive, 2x plus 1 is negative, and then x plus 2 is still positive. So again, this guy up here, it turns negative once I cross over this 1/2. It'll be negative the rest of the way down the sign chart. Positive times negative divided by positive is negative. Okay, let's roll across x equals -1 here. So now this factor right here, x plus 1, that turns negative. So I have a negative times a negative divided by a positive. That gives me a positive output. Last but not least, let's roll across x equals -2. This factor now turns negative. So I have a negative times a negative divided by a negative. It gives me a negative result. So this sign chart flips from positive to negative to positive to negative. And most of them that we look at do that, but not all. So please be very careful when constructing a sign chart. Sometimes you could have positive across something like a 0 if the behavior, if the graph bounces at that 0. All right, if you guys don't mind, I'm going to erase this stuff right here, just so it doesn't get in the way of our graph. This guy too, we got to get rid of that. Okay, now I'm going to add some axes and graph this thing. All right, so I have my axes set up. Let's go ahead and mark our asymptotes. I have a vertical asymptote at x equals -2. That'll be right there. I also have a slant asymptote. So how are we going to mark that? Well, the slant asymptote is 2x minus 1. First thing I'm going to do is I'm just going to mark some points on that line. I'm going to have a y-intercept of -1. Try that again. Y-intercept of -1. I'm going to have a slope of +2, so it's going to rise 2, run 1, rise 2, run 1, rise 2, run 1, rise 2, run 1. So we can see that behavior there. I could also think of it as rise -2, run -1, rise -2, run -1, rise -2, run -1. So there's enough points there for me to kind of graph that slant asymptote. It's going to look like that. Okay, and remember, that is an asymptote that our graph will not. The slant asymptote shows us the end behavior of the graph. So the graph will not cross that asymptote out at the ends as x goes towards positive or negative infinity. Okay, the graph will approach that but not cross it. All right, so let's keep going here. What else can we do now? Well, we've got some points on this function that we can graph. Okay, we've got an x-intercept at -1/2. We have a y-intercept at 0, 1/2. We also have a hole. Don't forget, we have a hole at -1, 0. So that hole and that x-intercept are pretty close there. Use caution. Make sure you're very careful with those two. Okay. Now we're ready to graph this thing. We have to look at our sign chart. As x goes towards positive infinity, my graph is positive. It doesn't turn negative until between 1/2 and -1. So that's going to be tricky to graph here. positive all the way from 1/2 to infinity, which means my graph is going to look like this. It's going to approach my slant asymptote as I go off from 1/2 towards positive infinity. And then it's only negative for a very short period of time, like that. So it's negative between the x-intercept, and that might be something useful to write in here. That's an x-intercept. It's only negative between the x-intercept and the hole, and then it turns positive again. So my graph turns positive after that hole, and it's got to stay inside that vertical asymptote. Okay, so let's look at what happens on the rest of the graph. After we go to the left of the vertical asymptote at x equals -2, my function is negative. Well, here's my vertical asymptote, x equals 2. Here's my slant asymptote. I can't cross that, and I have to stay negative. So the behavior of the graph down here is going to look like that. Interesting. Okay, folks, so I'm going to encourage you to take a look at your graphing calculator and make sure you get the same image as we just sketched out right here. And again, this was the line y equals 2x minus 1. It was our slant asymptote. And this line here was x equals -2, which was our vertical asymptote. That's it, folks. Hope you have success when graphing rational functions by hand.